Okay, let's carry on with October, November 2025, paper 42, 2 hours. Question 4. Right, there's your question 4. Right, be careful when you state the first law, not only the second part, which is usually what the teacher will be teaching you, but the first part also. Right, to show there is conservation of energy. Okay, we have done this part. Right, basically, PV, P volume times pressure. Get it from the graph for A, and then A you can read from here. U is 18. Okay, and then replace the XY here. Right? If they ask you to derive lah, then that is how you derive it. Okay, we will stop here. So, in an ideal gas, the thermodynamic temperature T contains N molecules. Use your information in B1 and the equation of state for ideal gas to deduce an equation for U in terms of N and T. Identify any other symbols used. Right? That's how we derive this equation from here. Then equation of state. K is Boltzmann constant. Right? PV, replace the PV here. Right? It's 3/2 NKT. Determine the expression in terms of X and Y for work done on the gas during AB. AB, constant pressure, work done. P delta V. Right? P is constant pressure 2Y. Right? From 6x to 2x. So it's 8xy. And CD CD. This is work done by the gas. Then the formula P delta V, right, 5y from 2x to 6x. Right? It's work done by the gas is negative lah. Use the answer in C and the first law of thermodynamics to determine the expression in terms of X and Y for the net thermal energy Q applied to the gas during the full cycle ABCD. Right? Full cycle. Explain your reasoning. Right? That's the first law. Work done during the stages B, BC, BC, and DA, right? Constant volume, so no change in volume. So work done is 0. And QBC, UBC, right? We are just using the first law. No work done is 0. So it is equals to internal energy. QBC equals internal energy, UBC. Right? There's a increase in temperature lah. Then QDA, right? QDA, no work done also. So it's also equals to Q, QDA, right? Except that there's a decrease in temperature lah. That's why there's a negative sign here lah. QCD, right? W work done along CD is that, and then Q1, right? We calculate Q1 for here, QBC, QAD. Now we calculate Q1 for here, right? Using the first law, is Q, right? Q minus W. So it's Q delta UCD, right? There's a expansion, right? That's why minus becomes positive, right? There's a minus here, there's a minus here, becomes positive. Right? We're still using this formula, except that you have to be careful, right? Q2, right? Okay, for AB, put down in AB, Q2, using the first law, right? We just take the W across there, that's all. So that's why we get this one. Okay, this one there's a decrease in temperature, right? Negative sign there, and then minus W minus 8xy. The red one is the one they will give the mark, that's all. They won't give you mark for all the other working. You have to use the other working to get your final answer. Change in internal energy over a complete cycle is zero. That's important. Because it starts at the same temperature, it ends at the same temperature. So there's no change in internal energy. Thermal energy supply is QBC, QDA plus all the Q. Okay, and all the U add together and subtract together will get zero. That's what it means here. So you end up with only this one, 20 minus 8x. Okay, Ken? Anything not clear?
No.
Okay, won't bother about this part. Okay, simple harmonic motion will come out every year so far. And then simple pendulum is a common one. A steel ball on the end of a thin string oscillates with a small oscillations, as shown in figure 5.1. The displacement of the center of the ball from the equivalent position is x. Right? These are the formulas in the formula sheet. The displacement of the center of the ball from the equilibrium is shown. Right? That's your x. Figure 5.2 shows a variation with x of the acceleration of the ball. Right? You cannot see, just draw it out carefully. Then you can see where is the origin. Explain how 5.2 shows that the oscillations of the ball are simple harmonic. Okay, you want to try without looking at the answer? Be a bit louder. Can?
I mean, I said that like the acceleration and displacement are directly proportional.
It's just a definition. A is x. A is proportional to x. That's the first step. is a straight line passing through origin. And then the other one is A and X are negative, right? Or X and A are in opposite direction to each other. So straight line pass through origin shows that A is proportional to X. Negative gradient shows that A is always in opposite direction to X. Right? These are the definition of simple harmonic motion. Right? From the graph, you can get your maximum acceleration in magnitude, maximum amplitude, right? Which is that one there. Determine the period. Right? That's what we can get from the graph. Right? Go to the formula, given in your data sheet. Okay, and remember, use it. Right? Negative show direction only, so don't have to worry about negative sign. Right? Substitute in your equation. We're going to find omega first. So it's 13 divided by 1/2, square root 8. And period is 2 pi over omega. 2 pi omega is at what value? 1.9 second. At time t equals 0, when the displacement of the ball has its maximum value, the ball is immersed in a trough containing thick oil, so that the ball is just below the surface of the oil. The result in subsequent motion of the ball has been heavily damped. What is meant by damping? Okay. What's meant by damping?
Lots of energy of oscillations due to the resistive forces.
Due to what?
Resistive forces.
Okay. 2 points. Due to energy of oscillations due to resistive forces. Force or forces. On figure 5.3, sketch a possible variation of displacement x of the ball at time t equals 0 to t equals to 2t. Right? Remember, this is your value for x and a. So x naught is 1.2, the maximum. So that's how the graph look like. Right? They will look at the amplitude, correct or not? And then they will look at the period. That's a period. We start with a cosine curve because here the pendulum is displaced in to the maximum amplitude and then release. Okay, any comment? There's the marking scheme for 3 marks there. How you get your 3 marks? Okay, anything not clear?
Oh.
Okay. Define electric field at a point.
Electric field at a point. Force per unit charge, positive charge.
Okay. Force per unit positive charge. An isolated conducting sphere in vacuum has a capacitance of 59 picofarad and the charge of the sphere is 86 picocoulomb. On figure 6.1, draw few lines to represent the electric field outside the sphere due to charge in the sphere. Okay. If positive charge, the field line should be going up lah. And then all of them as if they originate from the center of the sphere. Right? 4 lines, you want to draw more, can, but no need to draw too many lah. Right? Radial line, that's the first point. Arrow pointing away from the sphere, second point. Calculate the electric potential at the surface of the sphere. Right? There's a formula sheet.
Then use the C equals Q over V.
Okay, C is Q over V. Lor. Put in your calculate your V is Q over C. That's your C. That's your Q. And calculate out lor. 1.2 volt lor. Determine the radius of the sphere and use this formula lor. Don't worry about the way I do it lah. I try to simplify the step lah, but again, just use this formula lah. Just use this formula is correct. Right? I'm just using this formula, that's all. Lazy to calculate. And then 1 over 4 pi. 1 over 4 pi is 8.99. Right? And C is just that. That's your C. Okay. Don't follow me. Just use the formula, this one. If it's too complex. Previously, they asked you to derive this formula lah. This formula. Right? A sphere is a capacitance also. A capacitor also, sorry. Okay, the electric field strength at the surface of the sphere. Give a unit for your answer. Okay, this is what we have calculate R and V. Right? This is the formula. Right? Basically, Q over 4 pi epsilon R is V, and there's another R there divided by R, just to simplify the step lah. If you don't want to put in the value, same thing. The sphere in B is discharged by connecting it to the earth through a resistor or resistance 12 mega ohm. Calculate the time taken for the change to 4 to 26 picocoulomb. Formula sheet, if forgotten the formula, use this formula. Right? You are working with charge, so put charge. Time constant, RC. R is change it to SI unit. C, that's your C. And use this formula. Ln Q is 26. Initially is 83. 3. Right? Same unit, so they cancel out, doesn't matter. No need to convert it to SI unit. And then you take ln of it, this becomes your T over that. That's the RC. From there can calculate your T. Can? Okay. Alternating voltage varies with time T according to the formula. V is in volt, T is in second. For the alternating voltage, show that the period is compared with the standard equation. V is V naught cos omega t. Omega is 40 pi lor. And T is 2 pi over omega, 2 pi over 40 pi lor. Determine the root mean squares voltage. Right? Just memory work. Root mean square voltage is V naught over root 2, 18. That's your V naught. Stop me if I'm going too fast. On figure 10.1, sketch a variation with time t, v, with time value from t is 100 millisecond. So you have no choice. Sketching graph is compulsory. You have got the answer value. So value of amplitude is 18. That's your period. So it's a cost graph. Okay.
Okay.
That's what the marking scheme required for your 3 mark. The alternating voltage is rectified to produce the output voltage across the load resistor as shown in figure 7.2. Figure 7.2 shows the variation with power P and the load resistor. Remember, it starts from 0. It starts from halfway there. It starts from 0. Stage 3 conclusion that can be drawn from figure 7.3. Conclusion can be qualitative, can be quantitative. Quantitative, you have to calculate out lah. Use the space for any working. Right? Rectification is full wave. Right? Peak voltage is 28 watt. Mean power is 14 watt. Period of output or period of output voltage or power is 25 millisecond. Right? 25 millisecond. Right? These are the other possible answer that they will accept lah. Right? Make sure you know how to calculate the others. Right? That's how you calculate your R from this one. V naught square or V naught. Right? 12 ohm. I root mean square, V root mean square over R. 13 over 12, 1.1 m. Frequency is 1 over period. Okay? That's your period. Yeah, accepted. Anything not clear? Anything you need me to explain further?
Okay.
Okay. Next part is something new lah. Never come out before. So far, they will give you this one. You're supposed to calculate this one, and this one. No? Okay, based on this one. No? There's your N1, N2, N infinity, and infinite is 0 volt lah. So this is negative lah for hydrogen. You don't need to know. Basically, it's ultraviolet lah. The next one is visible lah, but you don't need to know all of them lah. Okay, know how to calculate. Okay, figure 8.1 shows the 3 lowest frequency line in part of the emission spectrum of hydrogen that relates to electron transition to the ground state, level n equals to 1. Right? These are 3 lowest frequency lah. So basically these three lah. These three lah. Right? This level, that level, and that level lah. The numbers represent frequencies in 10 to the power 5, 15 Hz associated with the spectral line. Use the photon model of electromagnetic radiation to explain how the existence of spectral lines in the emission spectrum provide evidence for discrete electron energy level in the hydrogen atom. Okay, you want to try?
Don't really know the answer for this one.
Electron moving from between levels emit single photon. Energy of photon is a difference in energy between energy level. Energy of photon depend on frequency. Right? These are other points that they are acceptable lah. Right? Basically, they are saying is right? This energy level are discrete. So this energy as it goes from higher energy level to lower energy level, it emit a specific wavelength. Same here. Okay. Anything still not clear?
Okay.
By there, then you calculate, no? Energy near ground state, n equals 1 is this one. Calculate the energy draw the ground state. Right? 1 electron volt is 1.6 and 10 to the power minus 19 joule. 13.6 electron volt is 13.6 times 1.6 and 10 to the power 19. That's 2.18 and 10 to the power 19 joule. So the energy difference between N1 and N2 and N3. N1 equal N equals 1, N equals 2 is 10.2. So this is the first one. Right? This emitted from N equals to 2 to N equals to 1. This N equals to 1. Right? That's the formula. So this energy level 2 to energy level 1. This is a frequency that's emitted. That's a frequency emitted. So we calculate the difference in energy level. Right? That means we are calculating this energy level, the difference in energy. Right? We are calculating this one. Okay, page is 6.63 and 10 to the power minus 34. And then frequency, right? The lowest one. Okay, only 10 more minutes lah. So that is your that. And 10 to the power 15 lah. And calculate out lah. Right? There's a change in energy level we have calculated. And E1 is 13. This one. E2 is this one. Okay. Any comment?
No.
So same lah. Calculate for the others. So then fill up. Yep. Any comment or anything you need me to explain further?
No.
We still got about 8 minutes, just to let you know in case we get cut off again. State what is meant by mass defect of a nucleus. Okay, you want to try without looking at the answer?
Mass defect. I wrote difference between the mass of nucleus and the sum of individual nucleus separated to infinity.
Okay, different
Nucleons.
mass of nucleus and the mass of constituent nucleons when the nucleons are separated to infinity. The nuclear fusion for the formation of helium from deuterium is represented by the equation. Table 9.1 shows the mass of nuclides involved in the reaction. Calculate the energy released in the formation of 1 mole of helium-4. Okay, delta M, hydrogen, right? 2 of them times 2 minus helium-4. Right? There's a total mass of the reactants. There's the mass of the product. Get that? Then right, convert it to kilogram. Right? Use your data sheet to get this formula. Kilogram. Then energy release is per atom is delta M times C square. Right? That's your delta M. That's your mass. That's your speed of light. Square that to get the answer. Then 1 mole contains 6.02 times 10 to the power 23 atom. The energy released in 1 mole is just that value times 6.2. So you get this answer 2.3 times 10 to the power 12 joule. Anything that's not clear? Yep. Okay.
Okay.
You try to combine as far as possible. They try to test all part of the syllabus. So they combine. Nuclear will come out every year. So they combine with astronomy. The star Sirius has a radius of 1.1 times 10 to the power 9 meter, loses mass due to nuclear fusion at a rate of that, assuming that the power of radiation emitted by the star is equal to the power released in this process. Determine the luminosity of Sirius. Give your unit for the answer. What's luminosity? Can you remember?
Energy.
Not energy.
Wait, no, power. No, power.
Total power. Okay, total power or total energy divided by time. Total energy is delta M over T squared and delta T. Delta M over delta T is given. Speed of light square. Okay, so its total power unit is what? Use your answer in C part 1. Determine the surface temperature of Sirius. Right, you calculate L, so go to this formula. Right, you just substitute your L. That one is get from your data sheet. And then R is given. Right, is your R. Okay, anything need me to explain further?
No.
Explain how cosmologists use standard candle to estimate the distance of galaxy from the Earth. Ah, popular question. Okay, you want to try?
Okay. So I wrote the radiant flux density is measured on star, and then apply the formula F equals 1 over 4 pi d square to calculate distance between the galaxy from Earth and Earth.
Okay. Standard candle have known luminosity. This one is known. We can measure it. Radiant flux density from the star measured on Earth. Then we use this formula. Right? We can measure this one. This one is known. Then we can calculate our R. State what is meant by contrast in X-ray image. Yep.
Just,
Can
I mean, like how do you call it? The difference in degree of like blocking, I think. Blackening,
blackening.
blackening.
Difference in degree of blackening. Right? Just a negative photograph. X-ray or intensity I naught. That's your I naught. Is incident normally on the structure as shown in figure 10.1. That's 10.1. Material P has a linear attenuation. Right? That's your material P. Even linear attenuation. X-ray emerging from the structure in the region A has intensity of 0.053 I naught. Right? That's your A. Right? Use this formula, same as radioactivity. Show the intensity of X-ray emerging from B. B is I naught. So use this formula. There's your copy, and there's your total length, 5.8 for the answer. Determine the linear attenuation for Q. Right? Remember, this is given. That's given there. And then each of them will have an exponential there. Right? This one, combine these two together, that distance, and this 2.1. 2.1, this is 5.8 minus 2.1. I give you the answer in case you get cut off.
I think we're about to end already.
This part is not fair. It's not mentioned